Good afternoon, reInvent. My name is Ryan Burke. I'm a Senior Solutions Architect in the IoT organization of AWS. I'm joined today by my colleague Ashish Bajaj, Software Development Engineer, also in IoT Services. This is IOT309, combining IoT and machine learning for predictive maintenance solutions. So a brief overview of today's session. We're going to introduce the topic of predictive maintenance with a definition and value proposition. We'll discuss some of the challenges that would occur when you combine IoT and ML projects together, and then go in depth with a technical demonstration of a solution that we brought today. And finally, we'll close out with a summary of kickoff questions to ask yourself and ask your teams at the beginning of a new IoT ML project. We'll provide some resource links to check out for our solution and some resources for further learning. I don't know if any of these tracks are still happening in the future. I think this was also closing by the time we get out of here. So we'll just get right into it. So one thing to note is that all of the resources that we'll be reviewing with you today as part of our solution are available in a GitHub repo that's live already. It'll include the Jupyter notebook that we'll be walking through. It includes a CloudFormation template to deploy the solution to your account. We're super interested in any feedback that you have on this solution. You can reach out to us via the GitHub issues in that repository. So to get everyone on the same page, let me provide a quick definition of predictive maintenance. What are we talking about here? We're describing a solution that actively monitors the performance of operational equipment, typically in the form of physical sensors and process variables. The solution will use some kind of model to translate telemetry into a prediction of when that equipment would next need maintenance, and some actionable window of time for the maintainer to respond before a failure event might occur. The solution should also alert the maintainer automatically and potentially intervene itself if failure is imminently detected and could be avoided. So if we use an illustrative example, and we'll be using this kind of air filtration example throughout the session. Let's say we have an air filtering plant where equipment parameters need to be manually adjusted to keep it operational based on observed levels of air pollution for the current day. So every day a person would measure the pollution level. Maybe they get it from a feed, or they have some telemetry capturing the air pollution on site. Then they would offset equipment parameters for that air filter based on some past experience or documentation or a run book. The equipment would then be adjusted to operate efficiently for the observed pollution level for the day. And every 45 days or so, that air filter would get inspected by a maintenance team, and they would assess whether or not that filter needs to be replaced. So what are some problems that we can tease out of that description? Well, for one, each step in the process is highly manual and needs availability from a team member in order to take action. So what happens when priorities shift for a day and a team member is unable to complete the scheduled activity? Manual measurements are also subject to higher rates of errors from equipment misuse or maybe typos during data entry. Second, the more time between measurements can lead to increased risk of changing air pollution and operating conditions. So if you take a single daily measurement, you might mean you're setting equipment parameters based on just one observation instead of taking into account everything that we know about the past of air pollution in that area and some of our forecast. And third, scheduling maintenance on a predetermined cycle like that 45 days may be costing your business money to service equipment and change out parts that aren't yet needed, just to stay ahead of known failure rates based on, say, tribal knowledge or best practices. So we see the business value of predictive maintenance directly addressing those problems. The benefits are reducing spend on maintenance activities by scheduling them in a window balancing necessity and convenience for your team. It helps remove the dependency and some of those errors that you get from manual effort and manual activity. And it reduces, or it can help reduce unplanned downtime due to unforeseen malfunctions. So in the solution that we are demonstrating today, we will show you how we are using air pollution data to recommend equipment parameters and predict when an air filter will reach end of remaining useful life. So we'll be looking at air pollution data from a public data set that captured hourly air pollution and weather data from the US Embassy in Beijing starting in 2010. I think there's about 5 years of data in that data set. The link on the slides will direct you to that data set. It's also easy to get to from our GitHub repository. So this data arrives via IoT Core, where we're publishing it up from a Greengrass-based solution. It's stored and processed through IoT analytics, and then we train an LSTM model from that data. The model is then forward deployed to that IoT Greengrass Edge solution, where new measurements are used to make local inferences and help us retrain the model over time. So what we're doing is we're determining the future forecast of air pollution in that data based on an LSTM model that we trained from the air pollution data. And then that air pollution forecast would tell the operator, based on their run book, what equipment parameters to set that air filter to run for the day, right? And that's going to be better than just taking the current air pollution value or yesterday's air pollution value, because we're able to predict what it's going to be over the next day, right? So the actual process of configuring the air filtration equipment, right, those parameters are outside the scope of this solution, but it would be the logical next step once we get values from this solution. So in our architecture, I'll start from the sensor that you can see in the upper left-hand side and work clockwise. So this solution uses an EC2 instance to host our Greengrass solution, and then we simulate an IoT sensor that's getting this air pollution data from our data set. And at first, we're going to rapidly ingest that 5-year data set of air pollution data. It's going to get broadcast up through IoT Greengrass to IoT Core, and it's going to land in IoT Analytics for cold storage. Then from our notebook in Amazon SageMaker, we'll ingest that data set, or a training sample from that data set, use that to build our LSTM model. Once trained, we'll store that model in an S3 bucket. And then we'll bring that model in as a new machine learning resource back into our IoT Greengrass solution. We'll redeploy so it's available locally with a Lambda function that knows how to make inferences from that model. And then new data points that are being generated from our IoT sensor with the air pollution data will be run through that inference model, and it will tell us, give us a forecast of what the pollution will be. And finally, in the center middle, or top middle, we've got IoT events. That's going to be our complex event detection service for this model, or for this solution. And that will tell us two things. One, when the consecutive number of inferences is behaving poorly, right? If our model is not behaving optimally in production, we can capture the number of times that we see a poor performing inference, say something over a 10% range. And then it will send a notification to the solution maintainer that says, hey, the overall solution is not operating as efficiently as we'd like. Maybe it's time to retrain the model or just take some other kind of action to triage what's going on with our solution. And also, IoT events can be used to signal the operator, the maintenance team, that a new maintenance activity is needed. So what makes IoT and ML projects challenging? Well, to start, it's less like IoT plus ML, and it's a lot more like IoT times ML. There are challenges on each side that reach across and impact the other and make it more challenging. These kinds of solutions are highly iterative in nature, which means it can be tricky to project total project duration and time to value. These solutions also need involvement from many different stakeholders across business units in ways that they may not have worked before. Just getting stakeholders from information technology, operations technology, business leadership, get them all in the same room and agree on project scope can itself be a non-trivial milestone. So to properly define and implement an IoT ML solution, you'll also need experts from across the persona landscape, like a data engineer, a process engineer, data scientist, domain expert, and so on. So basically what I'm trying to get at is, if you can solo an IoT ML project into production, you're either underpaid or probably doing it wrong. So speaking of that iterative process, I recently attended a data intelligence conference and learned about this process called the Cross-Industry Standard Process for Data Mining, or CRISP-DM for short. And as soon as I saw a picture of the lifecycle diagram, it struck me as heavily reminiscent of the IoT value flywheel. And so at each of these phases, you can get an understanding of the cross-business units that need to come together and the personas that need to come together in order to drive an IoT ML solution from scoping to deployment. And so as we go through the notebook, Jupyter Notebook for the solution, which is kind of the bulk of the presentation in the live demo, you'll get an understanding of defining the problem statement, which is our business understanding, diving into the data. Let's see what's out there. We don't know anything about the data before we jump into it and start evaluating it. Preparing data, which is the process of configuring the data that we have into the processed kind of data that we need to properly train an ML model. Then we'll go through the process of modeling, where we train the model and evaluate the performance of it. And then finally, we'll deploy that model into our production solution. Two things that I thought were missing from the CRISP-DM model that are relevant to the kind of IoT ML flywheel. One is I added a tail from deployment, kind of back into itself, a self-referential tail there, to signify the process of retraining a model once deployed, right? It's never really a done deal. Once you deploy that model, you're going to experience some kind of drift, whether it's in the physical parameters of the equipment itself or the physical world around it that it's sensing. You're going to be continually retraining and optimizing that model. And two, as the solution is deployed and you're using it, you're making inferences, you're going to learn new things about your business or about that solution. And those new insights that we generate can feed into new business opportunities to explore. So before we get into the live demonstration, I wanted to highlight a few of those challenges from the IoT and ML sides. Please note that these are by no means exhaustive lists of the challenges in these respective spaces. So in IoT, we'll talk about data acquisition, which is the process of converting analog signals and physical telemetry into digital telemetry. Data ingestion, how do we move that data from the edge into the cloud? And finally, model deployment, which is where's the optimal place to host the trained model in our solution. So on the data acquisition side, for an illustration here, we have a different kind of setup. We've got an electrical motor, and one of the ways that we can monitor and observe and detect the health of an electrical motor is from the vibration coming off of that device. So in this case, we've got a vibration transducer hooked up to the chassis of the electrical motor, and we're able to hook that up to a handset here and capture the vibration coming off of that device, right? This is an example of, again, a very manual process. I have to take the kit, walk up to the electrical motor, attach the transducer, download the logs, take it back to my PC and upload, over some kind of serial connection. In more sophisticated methodologies today, there are wireless vibration transducers that can be affixed to this and just constantly emit the vibration coming off of that device. But some considerations for data acquisition, what kind of data do you actually need to solve the problem? In this case, we're actually using air pollution data to solve the problem of how often do we need to service our air filtration system. So there's kind of an indirect relationship there. But we found that the model is very useful and is very accurate to help us plan that. Does the data already exist? In this case, yes. We were able to find an air pollution data set from the UCI website, and in theory we could have another sensor that's capturing air pollution at any given site, or we can talk to the weather company and use one of their APIs to get that data going forward. Do we have access to that data? In this case, yes. We have our data set or maybe a live feed from a local weather service. And if the data doesn't exist, what new equipment is needed to get the data? So if you find that you're trying to implement this or work on a solution and you don't have any data to work with, it can be very useful to think about, well, are there multiple vectors or multiple ways that we can solve this problem? If we didn't have access to air pollution, maybe we would go with the vibration coming off of that air filtration system. So you want to think about different ways that you can get the data. And finally, some common physical measurements in industrial workloads. One is vibration we talked about. There's also decibels, the sound being emitted from a device, heat, electrical resistance, and maybe even duty cycles. So in our solution, here's a quick peek of the kind of raw data that we'll be working with coming from that CSV. So of particular import to us are the first two columns of the time series or the timestamps. That's an hourly timestamp over about a 5-year period. And the second column is the pollution level. And this is measuring the particulate matter that's in the air at the 2.5 micron diameter size and larger. We'll also be using some of the other parameters in the data set to help us understand the seasonality of this data. Moving on to data ingestion. So in the realm of industrial data, the quantity of data that's represented in IoT can be rather frightening. So here we can see estimates for the global data generation rates of YouTube and Facebook. These are just estimates that I put together based on some answers I could find on Quora about YouTube and Facebook. And they generate an estimated 58 gigabytes per second and 46 gigabytes per second, respectively. So it's the amount of new data being generated on those platforms. And on the right, we have a measurement of a single Pratt & Whitney geared turbofan, which can generate up to 10 gigabytes a second of operational telemetry. So 2 of the biggest services on the Internet of People next to just one industrial device, right? So we can clearly see that the amount of data generated by industrial IoT could be tens or hundreds of orders of magnitude more than the Internet of People. The key takeaway is that not all of this data needs to be moved to the cloud for an industrial IoT ML solution to be effective, and that one of the main perks, in fact, is leveraging such a solution to minimize the amount of data that we need to move to the cloud. On model deployment, because models are compact in size once trained, inference requires a trivial amount of compute power. This means a model can be deployed anywhere in the span from the edge to the cloud. It could be co-located right on the device or a device right next to the device that you're monitoring. It could live at a gateway, supporting a few different devices, or at the edge of CloudFront with Lambda at edge, or it could live all the way up in the cloud. Really, the key drivers of where to deploy your model are going to be cost, round-trip latency, and the number of devices that model is supporting. And in our case, we're making the assumption that we have one air filtration plant with a couple different air filters on site that are all supported by a single gateway or single green grass edge deployment. And so we'll be deploying our model to that green grass solution. Moving on to the challenges of ML. Again, this is not an exhaustive list, but we'll talk quickly, and we'll go into more depth in the notebook as well about how to define features, how to select an algorithm, labeling data, and model maintenance, what to do after a model is trained and deployed. So when defining features, you want to focus precisely on defining your problem statement. What constitutes project success? This will help you understand what it takes to get to a V1 and what some of those iterative cycles might look like. I find it helps to break down the process you are trying to model until a team of 5-year-olds could understand it. So your goal is to translate the domain expertise into the ones and zeros that a machine learning algorithm could understand. So how would your 5-year-old domain expert understand that equipment service is due? And if you can express it that way, you're off to a good start in terms of figuring out which algorithm to use and what data to use. Another consideration at this stage is whether you are training one model for one device, a 1-to-1 ratio, or if the operating conditions of that device are unique enough that you need to train, whether the operating conditions are unique enough that you can do a 1-to-1 ratio, or if you can support many devices with one model. And so you might find that machines that are coming from the same vendor, built in the same year, deployed in the same location, can all bootstrap from a common training job, but they might experience drift uniquely enough or distinctly enough to benefit from a one model per device solution. The next challenge is how to choose the right machine learning algorithm for your use case. This is another area where having clear understanding of the data that you have and the problem that you're trying to solve can help you make a good choice. In this case, is it a case for supervised learning, or is an unsupervised learning algorithm acceptable? Do you have clean labeled data that you can use that shows when the device is operating in a healthy capacity? And do you have samples of when it was failing or about to fail, right? That's going to be a good use case for supervised learning, where you can train on both kinds of data and evaluate the kinds of results that you're getting. Are you trying to solve a regression type problem, or is it a classification problem? So are you trying to just get any kind of number in a range, or are you trying to coerce specific classes of values out of your machine learning model? There is a litany of public educational material to help you drive your hypothesis and test loop. AWS training and certification is one place to start if you're looking to develop some expertise in this area. If you've been in any breakout session this week, you've probably seen a link, at least one link to the training and certification site, and there's going to be one in this one too. And one new service that was launched this week in SageMaker that can help identify the right algorithm, at least to select and move on with, or at least your initial test loop, is SageMaker Autopilot. So with your test data, you can feed your test data into any number of algorithms that are supported by SageMaker. It'll tell you which ones are generating the most accurate fit. So you can choose one or more of those to start with and move on from there. So for the algorithm in our solution, like I said before, we're using LSTM. This is short for long short-term memory network. It's part of the recurrent neural network family. And it uses memory to track internal state. This enables processing sequences of inputs and makes it a great choice for forecasting upon time series data like the time-indexed pollution data that we're using today. And we'll cover this algorithm in a little bit more detail during our live demo. And just as a quick preview, we see some of this pollution data. We have maybe a rough idea that there's some kind of seasonality to it in the peaks and the valleys there. And the LSTM model will help us really determine the long-term periodicity and seasonality of our data. Labeling data. So for supervised learning algorithms, supplying labeled data for training can be a hurdle, right? What happens if you don't have any any documented failures, right, of what your equipment is doing? If all you have is just operating healthily, you may not have a good starting point there. So this is where your domain experts are going to be absolutely necessary to the success of the project. Learning from them how they recognize and predict failure can be utilized to synthesize or generate some sample data. And then from there, you can build out a training data set that combines the healthy operational data that you may have with some synthesized failure data and use that to bootstrap your initial testing and evaluation loop. And another offering from AWS that can help in this space is SageMaker Ground Truth, which can deliver a mix of human and machine labeled data to get you started. And finally, once you've got a model, it's trained, it's deployed, it's making inferences, you've got a good confidence score from that model, the story's not over yet. As operating conditions and physical environments evolve, your model needs to evolve with them. Whether the equipment itself experiences drift or your sensing devices drift from their last calibration, you can continuously drive retraining of your model based on the inference score performance over time. This results in two forms of alert mechanisms. So like we said before, there's one alert that would go to your maintenance team that says, hey, this is the action that you need to take in the time window that's prescribed. And another for your solution maintainer that says, hey, over time we've seen the inference score and the performance dipping over time. This is an area where your solution maintainer needs to take a look at it. And so for this solution, we're using IoT events with some simple event detector models. So for this one, we're showing the solution maintainer detector. And so in this case, every time we make an inference, we're going to send the inference ratio, right, the percent correct we were, up to the event detector. And if we see any inferences that are outside of a 10% range, we're going to increase a counter that we're tracking inside the detector model. And if we see too many poor performing inferences in a short period of time, we're going to flip to the next state, which is indicating that our model is performing inaccurately, and that will send a notification to our solution maintainer. And so we would have a similar one for the maintenance team that would be something similar like this. Maybe you have a couple different states to show escalation. It's not as binary as this one, where as we see that messages come in and our maintenance threshold is getting smaller and smaller, we might escalate up through first a warning and then a high priority alarm. So with that wraps up our introduction. We'll kick it over to Ashish for the technical demo.
Breakout session IoT309, and thanks Ryan for such a great description of opportunities that lie by combining IoT and machine learning. Predictive maintenance is one field where a lot of research is happening because a lot of industrial IoT is trying to leverage it to benefit from it. Before we start our demo, I would like to remind that this is a 300 level session, so we expect our listeners to have some basic understanding of AWS services, especially in IoT. Before we start, let's reiterate the business problem that Ryan mentioned in the beginning of the presentation. We have an industrial air filter plant where the operating parameters are adjusted based on the pollution reading during that time. A person would manually take these readings and based on some past experience and personal judgment would often offset these values. Based on that, the parameter is adjusted for the air filter. We want to automate this process because this is highly manual and prone to errors. We'll be training a machine learning model to predict the pollution readings, and based on that, we'll make inferences at the edge so that we don't have to always send the entire pollution data to the cloud. Let's take a look at what we are going to build today. We'll be using an EC2 to simulate a device. We'll be deploying Greengrass onto the EC2. We'll have a CSV stored on the EC2, which will be simulating as a device reading. All the data will be ingested via IoT core into IoT analytics, which will be used as a cold storage. We'll then query that data which is ingested into IoT analytics and use SageMaker to train a machine learning model on top of that data. The model is ultimately deployed onto Greengrass. We'll be using a Lambda to make inferences at the edge. Since we need to create few resources as part of this solution, we have created a CloudFormation template to automate that entire process. To save time, we have already deployed the CloudFormation template for you. Let's go to IoT console and take a look at the Greengrass group that is created as part of this CloudFormation. As mentioned, we'll be deploying our Greengrass onto EC2. Let's go to the Greengrass group and deploy it. It'll take a few seconds before the deployment starts and finishes successfully. Let's take a look at the resources that we are deploying as part of this Greengrass group. So we have two Lambda functions here, the data ingester Lambda and the inference Lambda. The first Lambda is used to ingest all the historical data that is stored on the CSV on the EC2 onto the cloud, and the second Lambda will be using to make inferences at the edge. It will be making use of the model that we'll be training as part of in the later half of our demo. As you can see, our Greengrass group has successfully deployed. Let's go and trigger the ingestion Lambda. So we are subscribing to a topic. This is the topic where we'll be receiving all the historical data. So once I publish a message onto this topic, Greengrass is actively listening to messages onto this topic. As soon as it receives a message onto this topic, it triggers the ingestion Lambda, and the ingestion Lambda starts sending all the historical data. As you can see, we have started receiving the messages from our Greengrass group. One thing to note here is, even though we are ingesting all the historical data at a much faster pace, it uses the same route that you'll be using to ingest your device data. The data which is coming onto this topic is redirected to IoT analytics via a rule. So there's a query which takes the data from this topic and redirects it to IoT analytics. As the data is being ingested into IoT analytics, we have created a data set as part of our CloudFormation template using which we can query the data. You can run the query by the Run Now option here. Once you query the data, you'll be able to see a preview of the data here. As you can see, we have ingested our historical data into the cloud already. Let's go back to it. So the UI you see here is Jupyter. It is our standard among data scientists to train machine learning models using Jupyter because it allows you to put code, illustrations, and diagrams in the same notebook. So the business people can see what is happening in the notebook while seeing at the code level as well. As you can see, we have deployed our Greengrass on the EC2, which is our simulated device. We have connected this Greengrass to the cloud using IoT core and ingested all the historical data into the cloud. We were finally able to query the data using IoT analytics. It's time to train a machine learning model using SageMaker. Before we start, we need to import some basic Python libraries into this notebook. We need to import libraries like pandas, numpy, keras, which is standard libraries for training any machine learning model. As you can see, we have successfully able to import all the libraries. Now the next step is to get the data which is queried in IoT analytics into this SageMaker instance. We can do that by creating a Boto client of IoT Analytics and calling this API from IoT Analytics. Let's do that. As we run the code, we can see some few rows of the data set that we have queried. As we see the data, the first problem about our data set before we can train our model is revealed. The pressure readings and the pollution readings, the value is significantly higher than the rest of the parameters. The way most of the machine algorithms work is by finding a hyperplane across different attributes, and in case few of the attributes' absolute value is significantly higher or lower than rest of the attributes, it creates a biasness in the model and makes the model inaccurate. We need to scale our attributes on the same scale before we can train a machine learning model. But before we make any other transformation onto our data, let's upload this data onto S3 so that we can leverage SageMaker training job to train our model. This allows us to use the dataset which is uploaded onto S3, use the SageMaker training job, and upload the model back to S3 in an automated fashion. We can do that by creating a SageMaker session and then uploading the data onto S3 automatically. Let's do some analysis on our data before we make any transformations again. We need to understand how our data looks like before we can select the right machine learning algorithm to train our model. We can do that by plotting all the columns of our data set. We can see visually that dew, temperature, and pressure has some seasonality in them. However, the pollution readings here doesn't have any significant statistical features. We need to dig further into the pollution readings here. We can do that by using a library called stats model. It allows you to decompose your data into trends and any seasonality part. Let's look at the first month of data to see if we have any trends or seasonality. As you can see, there are 30 humps in this seasonality, which indicates that we have a daily seasonality in our data set because it was the first month data only. However, we don't see any specific trend in our data set. So we can see there is a short-term seasonality in our data set, but is there any long-term seasonality too? We can do that by forcing our model, stats model, to decompose at a higher frequency than it was doing. Let's set the frequency at a higher number, and that will look for any seasonality which is bigger than a daily seasonality. Let's run this on the first year of data. You can see now there are 12 humps here, which indicates that we have a monthly seasonality too in our data set. This makes this data set a great choice to use LSTM model. LSTM model is usually good when your data set has both short-term and long-term seasonality. It also works when you have multivariate inputs. Most of the classical regression algorithms becomes complex to handle when you have a lot of inputs to predict only one single output. But however, LSTM model handles that seamlessly. So we had a problem in hand, which was normalization. We have figured out the right algorithm that we'll be using for training a machine learning model. Let's do the normalization of our data now. We can do that by using the min-max scaler from the Skylern library. We just need to mention the feature range that we want all the features to be scaled into, and it'll be able to scale all our features into that range. Now we have solved the first problem, which was scaling the parameters. We have chosen the machine learning algorithm. Now, because LSTM is a supervised learning algorithm, we need to transform our dataset into a supervised learning dataset. We can do that by adding a target variable. So the way our dataset looked like was all the parameters and the current pollution reading. We want to predict the future. So can we assume that this is the knowledge that I have and I'm trying to predict what is going to happen next? So I want to know what would be the pollution level in the next timestamp. We have written a small function that allows you to do that. Let's run this and take a look at the data that we have now. As you can see, it transforms our data into what was the reading in the previous timestamp and the target parameter, which is the pollution at the current timestamp. Or you can think of it as alternatively in the way that given the knowledge that I have now, what I'm trying to predict in the future. So all the parameters t-1 is the knowledge that I have now, and I'm trying to predict what would be the pollution reading in the next timestamp. Now we have 5 years worth of data. Let's split into 3 parts: the training data set, the validation data set, and the test data set. We'll be using the first 2 years of data as the training data set, which will be used to train our model. The next 2 years of data will be used to validate our model to know how accurate our model is. And the last data set, which is the test data set, we'll be using it on the edge to make inferences. We are splitting the data here into 3 parts. Now, LSTM model requires the input to be in a 3D format where the axes are samples, time steps, and the features. All the rows of your CSV becomes the samples, time step being how much you are trying to predict into the future, which is just 1 for us right now. And the third being features. We have 8 features here, as you can see. And the pollution T is just is the target parameter for us. Let's run this. Now, we need to define our LSTM model. So we are using a sequential vanilla LSTM model with 50 neurons in the first layer and 1 neuron in the output layer. We'll be using mean absolute error as the loss function and the Adam version of stochastic gradient descent as our optimizer. Mean absolute error allows you to calculate error disregarding the direction. We don't care if our prediction was high or low than the actual value. We only care by how much we were off. And the Adam version of stochastic gradient descent, it has other benefits as opposed to the classical stochastic gradient descent. It has an adaptive learning rate, so it can be compute efficient when you are trying to train your model on large data sets. It also has other benefits which you can read. We highly encourage you to try and play with these parameters and try to tune these parameters so that you can achieve better accuracy. We did some experimentation to reach at these parameters, but you can try to do more hyperparameter tuning. Now we have defined our model, we have scaled the parameters. It's time to do training on our training data set. We can do that by calling model.fit, give the train data set, what were the actual values. We'll be training it for 50 epochs and a batch size of 72. We can check how well our model was learning by giving a validation data set as well, which we are giving here. Instead of training our model on the data in this SageMaker instance, we'll be using a SageMaker training job to train our model. The benefit of using a SageMaker training job is right after the training job, SageMaker is going to package all the model artifacts and upload it onto S3 for you. It has a direct integration with Greengrass, so you can just select the SageMaker training job, and the Greengrass can automatically fetch the resources for you and deploy it. Let's do the training. It'll take around 3 to 5 minutes for the training to finish. In the meantime, let's take a look at the inference lambda that we have deployed as part of our Greengrass group, and that will be making use of this model. So as you can see, this is the inference lambda that is created as part of our CloudFormation template. And let's take a look at what is happening inside this lambda. So it reads the data. It loads our model, which is both the scalar and the LSTM model. One thing to note here is you're not just saving the machine learning model, you also need to store the scalar with which you scaled your parameters. You need to transform the data with the same scalar and then infer the data and send it to cloud. Let's take a look at what is happening at the infer data function. We read every row of the test data, call model.predict, and do an inverse transformation based on the scalar. We do that to get the output in the same units and scale as the actual values that was fed it before we scaled our parameters, and ultimately publish the results onto the cloud using IoT. In the IoT function, we are not just publishing the actual and the predicted value, we are also publishing the new data that is coming in, which is the test data. This allows us to retrain our model in case we are drifting away. This is usually essential if you're drifting away and you want to make sure you want to retrain your model to achieve better accuracy over time. Let's take a look if our model has successfully completed. It's still launching. It should take a couple of more minutes.
So we can see that there's some parallels, right, between the code that's in the notebook, right, to form our data into the right, shape to train a model, right?
Right.
And we're seeing the same parallels in the Lambda function itself, right? So what percent of the code is really truly different between the code to massage the data into the format we need for the training and the code that we need in the Lambda function to make the inference on the model itself?
The difference is not much. The only difference we are doing here is instead of calling model.fit, which we are calling in the notebook, we call model.predict. Everything else remains the same, which we are doing in the notebook. The same code goes into the Lambda. We are ultimately publishing the results onto IoT, which is not happening in the notebook. So that is the only code difference between the two.
So we're using the same structure and basically the same libraries between the two Python environments, right?
Yeah.
Okay. And tell me a little bit about the scale of data that we're using here. We have 5 years of hourly data. How does that stack up compared to the amount of training data that we would have in another industrial IoT kind of solution?
So we have 8 features here. You can think of it as the data coming from one single air filter plant. So in case if you have a huge industry, you'll have hundreds of air filters running. So essentially, you might need more. You might have a lot more data than what we are ingesting here. However, the entire pipeline would be the same. You wouldn't have to do anything. Right from the beginning, from IoT code to IoT analytics, we have ensured that every service is scalable enough to handle your hundreds or even thousands of air filter. And even in the notebook, we are trying to be efficient when we are computing. For example, the optimizer that we have used is the Atom, which is very efficient for large data set. So so customers can directly use the notebook even for their large data set that they may have.
We could take questions after the session closes, but yeah, we'll hang out around.
So as you can see, the training job has finished successfully, and SageMaker at the end of the training job uploads the model artifacts onto S3. It's time to fetch the model artifacts from S3 and see how accurate our model was. We can do that by using this function. It just fetches the S3 file and unzips it. Now, the model is in our local repository. Over here, it's time to load the model. Now, one thing we want to check is while training, did we overfit our model onto our training or validation data by any chance or not? So if you remember, we supplied the validation data set as part of our training. It's important to note down the history while training the model. Let's plot the history. As we can see, the loss and value loss of the training and validation data set. Initially, our model was learning very fast, and later it slowed down. The loss and value loss on train and test data is almost similar. This means that we have not overfitted our model onto either training or validation data set. If you see a huge gap between this orange and blue line when you are training your own models, it means you are either fitting your model on the training data set or on validation data set. Now let's use the model that we have loaded to make predictions on the validation data set. Now, accuracy in regression models can often be difficult to calculate because there is no ground truth. We want to check how much error did we have when we predicted a value from the actual value. We'll be using root mean square error, which is mean of the sum of squares and then square root of it to give you the final error in the same units as the actual value. We'll be using that as the standard to calculate how accurate our model was. So our root mean square error was roughly 27 here. But however, we cannot benchmark how well our model is performing. Like this is a number which doesn't make sense in its absolute sense. So we need to benchmark this number. We'll be using a persistence model, which basically says the value in the next timestamp would be the same as the actual value in the current timestamp. Let's take a look at the refactored data set here. So we know what the pollution at t-1 was, and the predicted pollution using the naive persistence model would be the same as the pollution reading in the last timestamp. And if I want to calculate the error using the naive model, it would be what I predicted and what the actual value was in the next timestamp. Let's calculate the root mean square error on the validation dataset using this persistence model. As you can see, this is also giving a root mean square error of roughly 27. So our model is roughly behaving similar to a naive persistence model. This is to note that we have trained our model just for 50 epochs, not very long, roughly for 5 minutes, and without doing any hyperparameter tuning. Also, our LSTM model was just one layer with 50 neurons and one output layer. You can make your LSTM neural network much longer to ensure you are achieving better accuracy on your data set. Now we have successfully trained a model using LSTM. It's time to deploy this model onto the edge using Greengrass. Let's go back to the Greengrass console and add this trained model as a machine learning resource onto it. So you can pick the SageMaker training job from here directly. This is the training which we have done right now. You need to mention a directory where the model should be deployed. We need to add some permissions to this directory so that our Lambda can access this directory. You can look at the Greengrass documentation to know what you need to do with the directory. We have created this directory as part of our CloudFormation template as well. You also need to affiliate a Lambda, which would be our inference Lambda, so that the Lambda can access the resources of the CloudFormation, resources of your model. Let's save it. It's time to deploy our model. As you can see, our deployment has started. It'll take a couple of seconds for the deployment to finish. In the meantime, let's go and subscribe to the topics where we'll be receiving our inference data. As you can see, we have successfully deployed our Greengrass group. We can trigger our inference Lambda by publishing a message onto this topic. Again, our Greengrass is actively listening to any messages which are published to this topic. As soon as it sees a message, it triggers our inference Lambda, which makes use of the machine learning resource that we have just attached and takes the test data and start inferring onto those records. Once we publish a message, you can see our Lambda is initiated and sending values of the predicted pollution and the actual pollution. One thing to note here is it's also sending the test data so that we can retrain our model in case our model is drifting. All the data which we are sending here onto this topic is redirected to IoT events using a rule again. So it takes all the messages from that topic and redirects to IoT events. So IoT events we are using for monitoring how well our model is performing on the test data. It's our solution for model maintenance. Let's take a look at the detector model that we have in IoT events to monitor the performance of our model. So we have two states here, model accurate, model inaccurate. When our predictions are 10% off than the actual value, and we make incorrect predictions for 10% on the total data, our model transitions to inaccurate, and we publish an MQTT topic. This is synonymous to saying that we alert some operator either to retrain the model or take manual control of setting the parameters. In case we retrain the model and it starts making accurate predictions again, it will transition back to model accurate. With that, I'll give it to Ryan to take it forward.
Thanks, Ashish. So to wrap up, we put together a couple questions to use in your own kickoffs as you're getting started with an IoT ML project. These will help you evaluate your level of readiness at that kickoff point. So, like we said earlier, is your problem statement well defined? Do you know what you are trying to achieve or what problem you're trying to solve? How would you describe success? What does success look like? How do you know when you're done, when you're close enough in your model performance? Who needs to be involved from the get-go? And very importantly, who is going to maintain the solution once it's deployed, right? We're working in a world now where IT and OT are coming to work together. OT is going to be the primary customer of that solution, and the maintenance team for the equipment. Are they also going to be the solution maintainer, or is IT going to be the owner of that solution? And do you even need to build your own predictive maintenance solution, right? You may want to check with your equipment vendor. They might offer an add-on or an upgrade to the equipment that you already have. Or maybe a third-party vendor would be more than happy to sell you a compatible additive or brownfield solution. And you can check the AWS partner network. We have a lot of partners out there who are working on these kinds of solutions. And that's because sometimes your business's defined time to value may not align with an internal build. So the demo that you saw today, it's hosted in GitHub. This link, you can take a picture of that. I'll leave that up for a little bit. The slides are also going to be made available. Also, there'll be a video on YouTube on the AWS channel. So a couple different ways to find this. If you go to GitHub, I think this one is hosted in the AWS-samples organization. And then if you search for any of those keywords, SageMaker Greengrass forecasting, it should come up pretty quickly. So feel free to tweak the model parameters or bring in your own data set. It is a reusable solution. Even if you're not doing industrial IoT or predictive maintenance, this is still helpful for bootstrapping a project where you're going to be ingesting IoT data, training a model of some kind, and moving that model back down to the edge for local inference. So it can be useful for bootstrapping any kind of project that fits those parameters. For further learning, we recommend taking a look at the IoT analytics and SageMaker documentation. There's also an existing blog that was written, I think, last year about how to build predictive maintenance solutions on AWS. Focuses more on kind of the IoT and IoT analytics side of the house. And then on the third thing here, we have another solution that was published this year. It's also about predictive maintenance and focuses a little bit more on the machine learning and SageMaker aspects. So you came to reInvent to learn. There's no need to stop when you go home. Keep reinventing with resources from AWS training and certification for IoT. Using videos and hands-on exercises, you'll explore a variety of IoT services. On-demand and digital IoT courses are convenient, available for free, and developed by the experts here at AWS. The popular Internet of Things Foundation series is a good place to start. There's 7 hours of on-demand instruction for anyone interested in the topic. So for more information, you can visit the website. It's at aws.training, and you can find the IoT courses in the learning library there. So I just want to say thank you for choosing to spend your time here with us today, this afternoon. We hope if you're coming from the IoT side, we hope you saw a little bit more on the ML side. If you're coming from the ML side, I hope it was a little informative to see how an IoT project works at the bookends of an ML project. Please, your feedback is very important to us. We want to be able to make this presentation and others like it more effective in the future. Check out the session survey and the mobile app and let us know how we can improve sessions like this one going forward. So we're going to wrap up, but we're going to hang out here in the room as long as we can have it, or we'll be out in the hallway to answer any questions that you might have. Thanks so much.